Now, at this point in our chemistry career as students, or any academic really, we've always seen our Lewis structures drawn like this. While there's nothing wrong per se with all those images and the quick way that you could do that in order to stabilize the octet, it wouldn't explain the expanded octets. Or wouldn't explain or guarantee that if you were to add up all those electrons, each of which carry a negative charge, that your entire molecule or compound is going to have a charge of 0. After all, isn't that why two elements will share electrons or transfer electrons? To stabilize a charge or to obtain a charge of 0, otherwise known in physics as a ground state. Now, when we draw these Lewis structures, we assume that all of the bonds made have the electrons equally shared between the atoms. And so under the assumption that the electrons are equally shared between every single atom that is bonding in a compound, if we added up all those charges of the electrons that are shared, would each element really have a charge of 0 like it's supposed to if it's bonding? To calculate what the hypothetical charge of that atom would be is something called the formal charge. The formal charge describes what the hypothetical charge is if we assume that every atom that your atom in question is bonding to has its electrons equally shared. And if we do the calculation and we see that our atom is not 0, even though it's got complete bonds, then that tells us that you're probably not looking at the best Lewis structure, simply because Lewis structure is based on the electrons being evenly shared between the atoms. After calculating the formal charge or the hypothetical charge, if your atom isn't 0, yet it's been bonded with something else, then it usually tells us that the Lewis structure we're looking at is not the best Lewis structure, and you probably either need to add a double bond or a triple bond in some cases. The Lewis structure that has all the atoms as close to 0 as possible is considered to be the best Lewis structure. So let's say we're asked to draw the Lewis structure for sulfur trioxide, which has the formula SO3. The first thing that we're going to do is we're going to write all the electronegativities that we find in the periodic table, and we're going to identify whichever one is the lowest. In this case, this is sulfur, and we're going to put it in the middle and bond all the oxygens around it. Once we've done that, we're going to count the total valence electrons that exist between the sulfur, which has 6, and the 3 oxygens, which each have 6 as well. And that's going to give us a total of 24. Remember to multiply oxygen by 3. Now, once we've done that, we're going to place those electrons around the non-center atoms. In this case, that would be the oxygen, right? The atoms that are not the center of this compound. And remember that each bond counts as 2 electrons already. So we're going to go 2, 4, 6 from the bonds. Then each oxygen is going to have 6 electrons on it. And we add until each of the octets are full. In this case, if we include the bond, that's 6 electrons for the oxygen, plus the bond that makes 8. And of course, 8 times 3 gives us the 24 electrons. Now what we're going to do is, with the distributed electrons, we're going to calculate the formal charge of each atom. And the formula for the formal charge is the number of valence electrons minus the number of bonds and minus the number of dots. And this is going to be done for each atom inside the molecule. So when we look at sulfur, we see that it has 6 valence electrons from the periodic table, minus the 3 bonds, each bond going to oxygen, minus, well, it has 0 dots. And so when we apply this entire formula, it has a formal charge of plus 3. Now, each of these oxygens look the same, but we're going to calculate for one of them and then show you that it repeats. In this case, oxygen has 6 valence electrons. It's going through 1 bond, and then minus, there are 6 dots, which I've highlighted here around the oxygen. And so when we tally up this, we get a formal charge of -1. And since the other oxygens follow the same pattern, well, all the numbers are going to be the same, right? They look exactly the same. So the second oxygen is going to have 6, -1, -6, that gives us -1. And the third oxygen also gives us 6 -1, -6, which is equal to -1. Now, since none of the atoms currently have a formal charge of 0, we're going to add bonds to make each have a formal charge of 0, or at least as many as possible. So when we make a bond, that is going to be to remove a negative formal charge. Okay, and we do that with 2 electrons. When we have a positive charge, we're going to receive a bond, and by receiving the bond, we get a negative charge, and that'll make it go back down. Lastly, every bond is going to be made with a lone pair, or 2 electrons side by side. So the sulfur with the +3 is going to need to accept 3 bonds, or 3 pairs of electrons. And so the oxygen on the right, or each oxygen actually, will give a lone pair or make a bond to the sulfur. And when they do that, they're also going to lose their negative. So when we look at the one on the right, it gives a lone pair. It goes from -1 to 0. And then the sulfur goes from +3 to +2. Then the one on the left also gives a bond, making the oxygen 0. And then the sulfur a +1. And then the one at the bottom also gives a bond, making that 0. And now sulfur is 0 as well. And so the final Lewis structure is going to have sulfur that is double bonded to each of the electrons. And one thing I want you guys to see here is that because each oxygen gave a bond away, it used up 2 electrons to give those bonds to the sulfur. Once we have each atom in the compound equal to 0, then we know that we have our final Lewis diagram, and you can smile. Now for the second example, we're going to draw the Lewis structure for hydrogen cyanide, or HCN. So like we did the first time, we're going to list all the electronegativity values of each of the atoms involved. And we're going to pick the lowest and put it in the center. So in this case, hydrogen is the lowest, but hydrogen already having 1 electron in its first shell will fill up after just receiving another electron. So hydrogen is special because after 2 electrons it fills up. So it's not ideal to put it in the middle because it could only make 1 bond. So hydrogen can never be in the middle. Again, especially in multi-atom compounds where you need to make more than 1 bond. So what we're going to do is we're going to go to the next best option, which is carbon. And so putting carbon in the middle and then hydrogen on the side. Now we're going to calculate the total number of valence electrons. So 1 from hydrogen, 4 from carbon, and 5 from nitrogen. And that gives us a total of 10 valence electrons. Now we're going to put them around the non-center atoms. But remember, hydrogen fills up after 2. So after that 1 bond, which counts as 2 electrons, it's not going to accept anymore. So we're going to put it around the nitrogen, which can fill up to 8 electrons. Now, like we did previously, we're going to calculate the formal charge of every atom. For hydrogen, it'll be 1 valence electron minus 1 bond that it's making with the carbon, and then it has no dot, so that'll be a formal charge of 0. Carbon's formal charge will be +2 as we go 4 valence electrons minus the 2 bond that it's making with hydrogen and nitrogen, and then minus the 0 dots that it currently has, so that'll +2. And then finally nitrogen with 5 valence electrons minus the 1 bond that it's making with carbon currently, minus the 6 dots that are presently in there, will have a charge of -2. Now, carbon being the charge of +2 is going to receive 2 bonds so that each bond can bring it down to 0. And nitrogen with a current formal charge of -2 is going to give electrons away so that it can go back up to 0. So the carbon and the nitrogen are going to kind of help each other out. So after doing this, you should have a triple bond with carbon to the nitrogen, and that would leave nitrogen with a lone pair still, and all the formal charges now are currently 0.